Hello everyone, my name is Alsup, and for this year's Innovation Day, I will be discussing the beta cell analysis pipeline my research partner Kelli Fowlds and I are designing. Our research focuses on predicting insulin secretion and beta cell images by utilizing deep learning algorithms. The study of beta cells can help further our understanding of insulin dynamics and better treat diabetes. Currently, the analysis of beta cell images requires hours of hand outlining, also known as segmentation, to obtain fluorescent intensities within individual cells. Additionally, many methods do not include linking cells frame to frame, forcing researchers to analyze intensities of an entire frame rather than isolating individual cells and tracking their signal patterns over time. We can track insulin secretion by introducing a fluorescent dye that will attach to calcium molecules within the sample. As calcium travels into the beta cell through calcium channels, insulin is released. We can estimate a cell's insulin secretion pattern through the amount of calcium shown through fluorescent intensity. Many beta cell studies track calcium signals over time, so a researcher will typically be analyzing multiple frames. This introduces a massive time inefficiency issue where one must outline multiple cells over multiple frames to effectively analyze insulin secretion patterns. Our main objective is to create a system that will automatically segment the image cells, track every cell across the time series stack, and output initial statistical analyses of the calcium signals. Our original outlined images and the subsequent masks can be seen in Figure 2. Our first step is to obtain beta cell images. The cells are cultured, loaded with the necessary fluorescent dyes, and manipulated, typically by the introduction of a drug or an electrical current. Our test image set has cells that are introduced to a 1 volt per centimeter current to study the effect of electricity on calcium channels. Next, we load our images into the automated script. Segmentation is performed by a validated, generalist, deep learning algorithm that will output 8-bit mask images seen in Figure 3b. Then, cells are linked across frames using a scripted third-party software. The original images are merged with the mask images that the tracking script will use to identify the cells and subsequently analyze intensities for every cell track. This step will output the raw data, which includes cell coordinates and the intensity of each cell from each frame, and an image showing the tracks as small lines overlaying the input image seen in Figure 3c. Statistical analysis begins by subtracting any background noise from the raw data, then normalizing the intensities. The normalized control and experimental data can be seen in Figures 4 and 5. Spatial and temporal data can assist researchers when studying any correlation in neighboring cells or identifying areas with biologically significant calcium signals. We can visualize areas with high calcium spiking with the Voronoi graph seen in Figure 6, and identify cell groups with high variance by utilizing the coordinate points given through the tracking step as seen in Figure 7. We have compared our normalized experimental data with normalized control data to verify our statistical methods. A p-value of less than 0.001 shows significant differences in spiking when a 1 volt per centimeter current is applied. Our future plans will include packaging all automated steps into one environment with all necessary packages preloaded. This will make distribution of the script very simple and require very little troubleshooting from researchers. We will also plan to use our pipeline to predict viable cells for islet transplants to treat type 1 diabetes by identifying appropriate calcium signaling patterns. Preliminary findings have shown beta cells growing in clusters may have a higher chance of being within the top 20% of signal variance compared to isolated cells. This suggests that cells growing in groups will signal more than cells growing isolated. As we continue our research, proving this discovery may greatly assist in islet transplants. This pipeline has the capability to lower the risk of failed transplants and will further provide the field with a valuable computational resource to significantly improve current treatment plans. It will also allow researchers to complete a full analysis of their beta cell experiments in a fraction of the time with more data. Thank you for listening.